Most people are running their GPU wrong, not because they don't care, but because nobody ever explained what any of these settings actually do. Ray tracing sounds impressive, so people turn it on. DLSS sounds like a compromise, so people leave it off. Both of those instincts are backwards. The setting most people ignore is the one that gives the biggest visual upgrade. The one everyone enables first is the one that tanks performance hardest. Stick around, because by the end of this video, you'll know exactly which is which, and your games will look better for it. Ray tracing. Let's start with the big one, ray tracing. You've seen the word plastered over every GPU box for the last few years, but here's what it actually means. Traditional game rendering is the technique that's been running your games for decades. It is essentially a giant optical illusion. It's called rasterization, and it works by projecting 3D objects onto a flat 2D image and then faking the lighting. Shadows are pre-baked. Reflections are a blurry snapshot captured from the middle of the room. It's fast, it's clever, but it's a shortcut. Ray tracing throws all of that out. Instead of faking light, ray tracing actually simulates it. The GPU fires millions of rays out from the camera into the scene. When a ray hits a surface, it bounces toward the light source, across a mirror, through a glass window. The result? Shadows that fall correctly, reflections that actually show what's behind you, light that bleeds realistically around corners. Here's a real example. Ever looked at a puddle in a game without ray tracing and noticed the reflection is just a blurry, distorted smear? That's because the game can only reflect what's currently on screen. Enable ray-traced reflections, and that puddle shows you a perfect mirror image. The building behind your character, the sky above, even objects that are completely off-screen. The catch? Ray tracing is expensive. We're talking a 30 to 50% frame rate hit in demanding games. That's why you almost never want to enable it without also turning on upscaling, which brings us to the next feature, path tracing. Before we get to upscaling, quickly path tracing. Think of ray tracing as selective. You enable ray-traced shadows or ray-traced reflections, but path tracing does all of it, everywhere, at once. Every single light interaction in the scene is computed physically rather than approximated. The results are jaw-dropping. Light that bounces off a red wall and casts a red tint on the ceiling. Sunbeams that scatter volumetrically through dust. Shadows with correct penumbras. But it is only for the most powerful hardware on the market, and even then, only with AI upscaling cranked up. Cyberpunk 2077's overdrive mode is the most famous example. If you have to ask whether your GPU, which means graphics processing units, can handle it, it probably can't yet. The next one is DLSS. DLSS. DLSS is the one that changes everything. DLSS stands for Deep Learning Supersampling, and it is NVIDIA's AI upscaling technology. Here's the idea. Instead of rendering your game at your monitor's full resolution, say 4K, the GPU renders it at a lower resolution, like 1080p. Then, DLSS uses a neural network trained on NVIDIA's supercomputers to reconstruct the full 4K image, filling in detail that was never actually rendered. And the results are genuinely impressive. In quality mode, most people genuinely cannot tell the difference between DLSS output and native rendering while picking up 50 to 60% more frames per second. DLSS 4, the latest version, takes this further with a new transformer-based AI model that's sharper, more temporally stable, and produces less ghosting on fast-moving objects than anything before it. If you have an NVIDIA RTX card and the game supports DLSS, you should almost always have it on. It is a free lunch. The only downside? It's locked to NVIDIA RTX GPUs. AMD and Intel users, hold tight. That's the next section. FSR. FSR, which means Fidelity FX Super Resolution, is AMD's answer to DLSS, and its biggest advantage is that it runs on anything. NVIDIA GPU? Works. Intel GPU? Works. A 5-year-old AMD card you're refusing to retire? Works. FSR started out as a simpler spatial upscaler, not as smart as DLSS, but widely compatible. FSR 3 added temporal accumulation, making it significantly sharper and more stable. And FSR 4, which is exclusive to AMD's newest RDNA 4 GPUs, uses full machine learning and genuinely rivals DLSS 4 quality. The same quality modes apply. Quality mode renders at 67% of native, performance at 50%, more FPS, slightly softer image. Bottom line, on an NVIDIA GPU, use DLSS if the game has it, FSR if it doesn't. On AMD or Intel, FSR is your best friend. Frame generation. Now here's where things get controversial. Frame generation. Upscaling cheats on resolution. Frame generation cheats on frame rate itself. Here's how it works. Your GPU renders a real frame, then, instead of your GPU immediately rendering the next one, frame generation steps in and manufactures a fake frame in between analyzing the motion between two real frames and interpolating what should happen in the middle. Your monitor sees twice the frames. Your GPU did half the work. The performance gains are massive. We're talking games that couldn't hit 60 frames per second suddenly running at 120. Cyberpunk 2077, with full ray tracing at 4K, goes from barely playable to genuinely smooth. But here's the trade-off people don't talk about enough. Those manufactured frames don't correspond to new input. So while your screen looks smoother, there can be a slight increase in input latency, the delay between moving your mouse and seeing it on screen. NVIDIA addresses this with Reflex, AMD with anti-lag. With those enabled, most people don't notice. NVIDIA's latest version, multi-frame generation on RTX 50 series, can generate up to 3 additional frames for every real one. That means up to 4 times your native frame rate. It sounds insane because it is. Use frame generation when your GPU limited at high resolutions. Don't use it for competitive games where every millisecond of latency counts. Dynamic resolution. Dynamic resolution is your GPU's automatic pressure valve. Instead of fixing the render resolution at a constant value, dynamic resolution monitors how hard the GPU is working in real time and quietly dials the resolution up or down to keep the frame rate stable. Hit a dense city street with explosions everywhere? Resolution drops slightly. Standing in an empty corridor, it snaps back up. It runs invisibly in the background, and most players never notice it happening. The only time it becomes visible is in extreme cases, a very aggressive dynamic range, or a low-end GPU pushed to its limits. When combined with DLSS or FSR, it's remarkably effective. Turn it on and forget about it. HDR. HDR might be the most misunderstood setting on this list. It stands for High Dynamic Range, expands the brightness and color range your display can show. A standard SDR monitor tops out at around 100 nits of brightness. A proper HDR display can hit 1,000, 2,000, even 4,000 nits in the brightest highlights, while simultaneously showing true, deep blacks. The result? A sunset where the sun looks genuinely blinding, fire that looks hot, shadows that are actually dark instead of just dark gray. Here's the catch. Bad HDR is worse than no HDR. Poorly implemented HDR washes out colors, crushes shadow detail, and makes everything look flat and gray. If you enable HDR and the game looks worse, that's a calibration and implementation problem, not HDR itself. Good HDR, properly implemented on a display that actually supports it, it's the biggest single visual upgrade available to PC gamers right now. Bigger than resolution, bigger than texture quality. Display sync. VSync, G-Sync, FreeSync. Screen tearing. That ugly horizontal split across your screen, where 2 different frames get displayed at the same time because your GPU and monitor aren't synchronized. VSync fixes tearing by making the GPU wait for the monitor to be ready before delivering a new frame. Clean image, no tearing. But if your GPU dips below your monitor's refresh rate, VSync forces it to drop to a fraction of that, 60 FPS to 30 FPS instantly. That stutter is often worse than the tearing. G-Sync and FreeSync solve this properly. Instead of locking the GPU to the monitor's refresh rate, they flip the equation. The monitor's refresh rate adjusts dynamically to match whatever the GPU is producing. Tear-free, stutter-free, no input lag penalty. G-Sync uses dedicated NVIDIA hardware built into the monitor. FreeSync is AMD's open standard and is widely supported. If your monitor supports either, use it. This is one of those settings that once you experience, you genuinely cannot go back. Anti-Aliasing. It's the jagged edges, those staircase-like lines on diagonal geometry that make games look like they were rendered in 2003. Anti-Aliasing fixes them. MSAA, the old standard, samples multiple points along each edge and blends them. Beautiful results, brutal performance cost. FXAA is a cheap screen space blur that smooths edges with almost zero performance impact. It works, but it also slightly softens the entire image. TAA, temporal anti-aliasing, has become the modern default. It accumulates samples across multiple frames to smooth edges at low cost, but can produce ghosting or blurring on fast-moving objects. In 2026, the best anti-aliasing is increasingly just DLSS or FSR themselves. They handle edge smoothing as part of the reconstruction process, and they do it better than any dedicated AA solution. If the game supports upscaling, that's your AA sorted. Anisotropic filtering. This one is criminally underrated, and almost nobody talks about it. Look at a road or a floor stretching into the distance in a game. Without anisotropic filtering, those textures go blurry and muddy the further away they get, viewed at an angle. It's because standard texture filtering treats every surface like a flat square facing you. It doesn't account for the steep angle you're viewing distant surfaces at. Anisotropic filtering fixes this by stretching the texture sampling to match the angle of the surface. At 16x, distant textures stay sharp and detailed no matter what angle you're viewing them from. Here's the best part. On any GPU made in the last decade, 16x anisotropic filtering costs virtually nothing. Zero performance impact. There is no reason not to set it to maximum in every single game you play, right now, and never think about it again. Texture quality. Texture quality controls the resolution of the image data mapped onto every 3D surface in the game. High quality means you can get up close and see fabric weave, skin pores, scratches on metal. Low quality means blurry mush up close. The limiting factor is VRAM, the memory on your GPU. Ultra textures can eat 8 to 12 gigabytes or more. If the game's textures exceed your available VRAM, it starts pulling from system RAM, and you'll feel it stutters, hitching, frames that suddenly freeze for half a second while data streams in. Set texture quality to the highest level your VRAM can comfortably handle without exceeding its limit. Don't just max it out blindly. NVENC. Last one, and this one's for anyone who records or streams their gameplay. NVENC is NVIDIA's dedicated video encoding engine, a completely separate chip on the GPU that handles video compression. AMD has the video coding engine, Intel has FreeSync, they all do the same thing. Normally, recording or streaming video is handled by your CPU, which eats into the processing headroom available for your game. NVENC offloads that entire job to dedicated silicon that isn't used for anything else. Your game keeps all its CPU resources. Your stream or recording runs in the background with zero performance impact. If you use OBS or any streaming software, make sure you're routing through NVENC, VCE, or FreeSync rather than software encoding. The quality is comparable and the performance impact is essentially nothing. And that's every major GPU feature actually explained. If this has saved you from blindly clicking Ultra on everything and wondering why your PC is struggling, drop a like. And if there's a specific setting you want me to go deeper on, leave it in the comments below. Don't forget to subscribe. See you in the next one.